that is the length. Of course, this length has to have something to do with so if the stream is like this, if the stream or the river, so that length of course has something to do with the length of the river. Or if you know, if for example you divert the it's not the dam is not exactly across the river, because sometimes you can divert the dam. So that depends on the length of the channel, whatever channel we are, the width, we should say, the width of the channel. So that determines the length of the dam. And so the structural height of the dam already shown. The structural height is the functioning height of the dam, the height for design basically. Then we have the maximum base of the width. You should see this maximum base width. The hydraulic height. So the structural height is the overall height of the dam, but the hydraulic height is the height of water, the effective height that uh, so let's see here, the effective height basically that water will so the hydraulic height of the dam is equal to the difference in elevation of the highest controlled water surface on the upstream of the dam and the lowest point in the riverbed. So the basically the height, the water height, the functional water height that will be uh, imposed on the dam. So forces acting on that. So because we should be able to design this. So we focus on the forces that you need to consider when you design. So of course we call them gravity dam because they are one of their we say mojo is a kind of a current a walk word, we can say. But one of the resisting, the mechanism they use to resist the lateral forces, the water pressure, or the forces that are supposed to carry the weight, the self weight, and hence they are called gravity dams. Number two, there is water. I think this is not should not be strange to you. We have uplift force, we have wave pressure, we have silt pressure, we can have ice pressure, we have wind pressure and earthquake. So you need to design for all these things. This is your dam, for example. So let's say this is your earth dam, for example. Okay, this is your earth dam, for example. That's your earth dam, for example. So now, of course, this is your water. So this thing has its weight. That's the point. And say this is your okay. This is your substratum. Uh, so this is the water. Of course, you know water would want to flow away this side, going this side. And if you draw your flow net, you should know this. Something like this. So then the pressure distribution, uh, this one has its weight, those components has its weight. The water, of course, if you are to draw pressure variation of the water pressure, uh, this is the variation. which is, this is rho g, not rho, okay, let me say gamma h, so that's the height. So all this pressure is acting on the, so this is the water pressure we've talked about. The self weight of the dam, you can see obviously. Uplift forces, because water would want to flow there. I think we already talked about this. There will be, and we already even knew a how to estimate this. You remember, you can get the pressure distribution here. You draw the, for example, the pressure distribution there is that, and the head loss somewhere there. Okay, let me use a different pen. If you don't remember this, you please refer to your notes. You can refer to the head there. You can calculate the head there, calculate the head somewhere there, and calculate the head somewhere there, and then you find some nice distribution, which you know the salient values are known. Then you know the length of the dam, and then finding the area of this pressure diagram, that would be the uplift force, you remember. So then you also need to find the factor of safety against uplift, because that factor of safety would be factor of safety against uplift. Against uplift would be the this force, the uplift force. Okay, so let's call it uplift. Would be the uplift force U divided by the self weight of the dam. So you remember this. So we talk about uplift. Of course, within the water here, there will be waves. All right. So silt pressure as well, because actually usually here you provide some controlled sizes of holes which you can close here. When you are desilting, you apply some pressure. So because the hole is here, the silts that are on this surface can be easily washed away and flow through this controlled channel. So there is silt pressure. The ice in places where we have cold temperatures, there could be ice. Then of course the wind pressure, the wind itself, the fact that wind will cause waves, that is one thing, but the wind itself will have pressure on the dam, the dam. Yeah, in fifth year you should have already known how to design for uh, horizontal loads on structures, like wind and earthquake, of course. And then there's also earthquake pressure. Of course, earthquake will come and will shake the dam, will move the dam back and forth. So you need to consider all these things. So each at a time. Those just coming in, please record your attendance. There's a cut on 28th. You can consult with those who are here before you. Now, the weight dam is the main stabilizing force in the gravity dam. I said this because actually it contributes to the stability, because you remember we said that the shear strength, or you should know, that color may not be very easily visible. So we said that shear strength is C plus sigma tan phi. Okay, let's be clear and say this is sigma V. So this sigma V will be contributed. So one of the component of sigma V is the weight of the dam. So this is the point. That's a point here. In fact, that's a point. So now the weight of the gravity dam by dividing the cross section. So these are just some geometrical stuff. So if, for example, the dam is like this, you can divide it into portion, maybe A. So this is A and this is B, and deal with them individually. So those are just sections whose area you can easily find. And that's the simplest. Of course, you can divide it into several other ways, but make sure you make your work simple. Again, you don't need to complicate. So this is the simplest, although I know some people might want to divide it like that and like this. So you have maybe this section alone, and you have this. So you can see in that way you have three sections. So you need to make your work simple. That's the point. But however you do it, those are just regular shapes whose area you can find, whose area you can easily find. Okay. So and then even for this one, this something like this, uh, you can find if you divide. This is just if you divide here, that's a trapezium. This would be a triangle. This is a trapezium which you can still divide and deal with them. Of course, I'm saying you make it easy. If I am the one working on this, then it's just easier to make the, because a trapezium you know already, so it's easy to divide. So this is a triangle and the rest is a trapezium which you can easily deal with, I'm sure. So that's the thing. So that's the idea. So the weight of the dam per unit length, so what we are doing, in fact, this is a cross section. uh, this is a cross section, so that means in the direction of the board. Okay, let me try to make what I'm saying clear. So if this is the, so if this is x, this is y, and this is z. So in the z, in the minus z, we are assuming in the z direction, that length is just 1 meter, is a unit. So that's why we are saying the length is equal to product of area of cross section times the specific gravity or unit weight, but we are saying per unit, per meter, per unit length. So when you are designing, basically you are designing for 1 meter, and this is assuming that the length, you remember we are talking about the entire length of the dam. So if the length of the dam is 30, this design is just per unit meter. So if you want for the entire dam, it multiply by 30. But this is assuming that the cross section is uniform, such that you can multiply by 30. If not, you have to divide to the sections that are similar, and then you multiply and add eventually to get the entire thing. Of course, for simplicity in these designs, we shall assume that the entire is homogeneous over the entire length. So just design per meter, and then you can multiply by the entire length of the dam. So the specific weight of concrete is usually taken 24, and that of masonry in 23. So these are fairly standard values that we know, so we don't need to worry too much. So this is the idea. So whatever it is, you can see we have the triangle there. This is just a rectangle, and that's just the triangle again, whose areas you can easily deal with from your geometry. So number two, the water pressure acts on upstream. The water variation on upstream phase is a main force acting on gravity dam. The raw pressure, of course, varies with depth of water and is expressed. I think this is pretty straightforward. So if this is the height, you need to get the maximum influence, or the maximum influence there. So if this is the height, then that pressure, and it's called P there, is simply water times the height of water to be specific. So gamma water. So very quite straightforward. Then is so P is the water pressure in kilonewton per meter squared. Gamma is the specific gravity of water, which is 9.8, and H, of course, is the measured depth measured below the free surface in meters. The forces actually not necessarily in meters. You can do whatever units you want, but of course standard units are in meters. Of course, if you measure in any other unit apart from meter, you have to also convert the unit of water, or the specific weight of water, to consistent units with the height, with the units of height. The forces due to pressure are discussed below separately for non-flow section and overflow section. So this is just laying groundwork for uh, the design later on. Those just coming in, please make sure you sign the attendance, record your attendance. So on the up, this one means up face vertical. So figure 4. So we see the figure first. So here they were talking about the upstream. Is upstream will be referring to this AB, and then downstream the opposite side. So let that be clear. So on the upstream face, the face AB of the dam is vertical. The total pressure is horizontal and is given by okay. This is you should know by now, or I believe you know. If you don't know, you should know that the to find, because we know, of course, that or we use the figure. Let's use the figure. Yeah, okay. Anyway, the figure is here. So this is the figure, the pressure diagram, such that this they use. I think they use some notations there, but you know that the pressure variation is such that the here they're using weight, but actually this should be gamma h. And then this is h. And to get the force which would be acting on the third is to find the area of the pressure diagram. You should be familiar with that. So the area of a triangle is just a half times gamma h times h. So you should not see difficulty why that is the case. So then that horizontal pressure is this that's this is the idea. So that's the force, and so and then acts horizontally at a height of h over 3 above the base of the dam. So this is on the upstream. Uh, so on the upstream surface face is inclined when the upstream face ABC is inclined or partly vertical and partly inclined. The force due to the pressure can be calculated in terms of horizontal component PH and the vertical component PV. Figure 5. The horizontal component is given by sometimes for this for a vertical face, but sometimes we have this can be inclined. The face AB can be inclined, or if not inclined, can be partially inclined and partially straight. So if that is the case, we can get the PV, this part, PV uh, in terms of horizontal, so D2 can be calculated in terms of the horizontal component pH and the vertical component PV. The horizontal component, so the is given by, so actually the same idea, the same, because for water it doesn't matter, the pressure is the variation is still the same. So for water the pH is just the area. PV is the this part now, the so just again the same idea, just the area of this. Also it acts at the, so this we're talking about h, also acts horizontal at a height of h over 3 above the base. The vertical component is equal to the weight of the water in the ABC. So the vertical component is the weight of water here, which again is just the area times the unit weight of water. So you can divide again this into regular shapes which you can deal with. Of course, this by itself is also trapezium. If you don't like that, you can divide into the rectangle and triangle. Be able to use your math skill to solve. So something is wrong here. Let's use the correct notation. So should be fairly straightforward. So if you need, you can, after you divide them into regular shapes, you solve each at a time, and then you can add. So PV is PV1 plus PV2. The lines of action of PV1 and PV2 will pass through the respective centroids. And if you want, in fact, to know the overall, I think you already know this. You should. If you want, so this the line of action is at the centroid of all of them. But if you want to know the overall so you find the area, you find some reference here at the bottom. I hope there is an example we shall use to demonstrate here. Then the force, of course, you know this one acts at of course 2/3 from this thin end. So the area, the force. So if you have calculated there, and this is, let's call it H1, and this is F1. The force you calculate here is F1, and the force you calculate there is F2. So A2, A1. Of course, you say that. So the force, you don't need the area. Force 2 times the distance to the bottom there is just uh, times h minus h1. So the distance there is the centroid is you divide that length by 2, of course, plus h1, because the reference, so reference is at the bottom there. All this has to be multiplied by that, plus f1 times 2/3 of h1. All this should be the same as f1 plus f2 times. So you don't know where the centroid is. I'm sure you have done this even in mechanics. So if say the centroid is somewhere we don't know, uh, x bar somewhere there which we don't know, x bar. So this is the same as, yeah, x bar, which you can solve because all this you should know. H1, all this you know. So that's how to find the overall centroid of the the force that of F1 and where F1 and F2 act at the effective center of gravity of this mass. So having said that, on the downslope, is shown in figure 5. Is figure 5. On the downslope again, so if the water is there, the variation is as shown. So for the water, the pH is the same. For this part, again, the PV is the area times the unit weight of water. So I think here is a problem. Is a problem as well. Some notation, a problem with the notations. So this, I believe, should be P. Just a minute. Should be pH. pH prime. Okay. So again, the horizontal component is the same idea. Yeah, the same idea. And then PV is the weight of the triangle KFG. The force PV acts on the centroid, of course, of the triangle. Obviously, when the water is depth H is 0, the water pressure, of course, is 0. So here we are assuming that the water. Okay, this is the most general of scenarios. That because of this flow, someone might wonder why again there is water on the lower end. But because, okay, let's use this one to explain. Please feel free to stop me if there's something that is not clear. So this is, if this is the substratum, let me use a red pen. And of course, because water is trying to flow to this end, so that's the idea. So if for some reason there is some water level there, then the scenario we're talking about. But if the ideal situation such that this height, the height here is 0, then the forces on the downstream are not there. That's the issue. That's the point. So the overflow section. So the section where water can flow over the dam. So on the upstream face, the vertical figure as shown. So if we provide, so this is your dam there, and then you expect some overflow of water. So this is the upstream we are saying. So shows overflow section, or this is the spillway of gravity dam with upstream face vertical. The water approaching the dam has a velocity va. The head ha. Some issue with the notation there. ha. Yes, okay. So now please make sure you record your attendance. So now the HA due to the velocity of approach, of course, you know this height from the kinetic energy that the water has, and this is a famous equation you should know from fluid mechanics. And the total energy line is height HA above the water surface. The horizontal component of the force due to the pressure of the dam is given by, of course, this is again the water pressure diagram. Again, some issue with the notation, which we need to correct here. My mouse, why? Yeah, so issue with the so this is again how to calculate the horizontal forces on the dam. So this is gamma. Okay, this is still about the area of the pressure diagram. So this you can see the rectangular the but now here let's go to the diagram itself. Here this the effective height, so H2. You can see here the total energy line there. So that's the reference. So you are only concerned of this part. And that's why you find the area of H2. No, not okay here. The difference, because the reference is here, so H2 minus H1, you can see so that this equation makes sense to you. So H and then HA is the you have to add because that's the energy, the additional height due to the due to the kinetic energy of the water. So you add HA plus uh, HA plus H1, but also note that the because you concerned of the height above the gravity dam, so this way it's H2 minus H1. Okay, and the rest is just multiplied by the density of the water. So you can see that. And of course you cannot forget the area of the pressure diagram of the water. So here, if you note, this is just like height. Remember, we were saying a half gamma h. If okay, you remember here, you check here. This is h squared. Now in this case, this h is h2 minus h1, but of course don't forget this other. So the total pressure pH acts at a height z above the base given by. So this has been made simple for you. Actually, you can do it yourself if you find the area of each of these. Just a minute. Using the same principle, I think I already demonstrated. You can find this effective point of application of the pH. So that's for the overflowing or the spillway overflow section. Inclined upstream face is as shown in figure. So the previous this is the vertical, but the face can also be inclined as shown in figure 7. Shows the so figure 7 shows the overflow section of a gravity dam with upstream face inclined. The force due to water pressure can be obtained from the vertical component and the horizontal component as in the case of non-overflow section. So due to the again. Okay, and the same idea here. So whether inclined or not, the force due to the water pressure will be obtained by the same formula we've already uh, uh, talked about. Now there is a dynamic pressure on the down slope as shown in figure 8. So here, no, sorry, this is figure 7. So figure 8, figure 8. So some dynamic pressure. The downstream face of the overflow section is usually of a curved shape due to change in momentum, and we want it curved so that we dissipate some energy, so that to avoid erosion of the because you remember we talk about the exit velocity, so we don't want the bottom of the dam to be eroded, otherwise with time you may no longer have the dam. So to change in momentum, the water exerts a dynamic force on the dam. The horizontal and vertical components of the force can be determined by applying the impulse momentum equation to water in the control volume ABED. The equation is applied in the horizontal and vertical direction. So to make sure we are clear of what you're saying, A B D A B. Okay, get the point. A B C D. So A B C D. So we take some section. Of course, the this is the surface of the dam, and then we take that section and it's blown there, and you consider the equilibrium of forces at the point, and from there you can get the horizontal force. I think this is not right. I mean the notation, something is wrong. The, something is wrong with the notation here. Yes, so the summation of the summation of the horizontal forces so where this is the sum of the horizontal forces and acting on the control volume in the horizontal direction, V2 and V2H and V1H subscript are horizontal components of the velocity at points 2 and 1. So if you're able to know the velocity again, and Q of course is the should be the discharge. Of course you should know that using the equation of continuity, V1. So if these ones you should know more than me. So if you have a pipe this way, so V1 A1 here should be the same as V2 A2. So because this part is larger, the area so here maybe V would be low here, V1 is low, but because that section is small, V2 would be higher. Yeah, so based on the equation of continuity, which you people should know better than me now, you can figure out these discharge issues. All right. So again, the in the horizontal direction, something is wrong. So that's in the horizontal direction, and this should be in the vertical direction. Is this thing acting uncontrollably? Yeah. So this is not horizontal. So this should be in the vertical direction. So this is, you can see that the equation is of the form of that in the horizontal direction. So should not be difficult to figure out. So where this again, some issue with the notation. Yeah, so where this is the vertical, some of the forces acting on the control volume in the vertical direction, V2, V1, and V1, of course, are the V1V, the of course with subscripts are the vertical, excuse me, are the vertical components of velocity at sections 2 and 1, respectively. So we have an example here to show. Determine the forces due to self-weight and water pressure on the non-overflow dam. So this is the section, the cross section of the dam. So solution, the weight of the section is divided into three parts. You can figure this out for yourself. I think it should not be an issue. The weight one. So weight one is which one is 42? Is 42? Weight one, yeah, okay, is this one. Weight one is this one. So this is a half base. The base. So you can see here. 42. Ella, sorry.
The base is 31.5.
The base, okay, base is 31.5, correct. And the what's this? Oh yeah, I can see. Well, the
The
base
pivot height.
depend on the, yeah. So you can take this one, okay, 24, 31.5, and the area. You're finding the area, and then times the unit weight of concrete. So you can see that for yourself, acting at 21 meters above. So from the toe, of course, this has to be just a minute. Weight of the section divided half base times height. Okay, so half base times height. I don't know which one you consider the times the what times the I mean the unit weight of concrete, and acting. I don't know why are we saying 21, but this is what this should be. Is it 21 really? Above here, this should act at a third, right? A third, 42 over 3, isn't it? No, no, no. Should act at, I think, a third from here. 42 divided by 3. Okay, let's see the next. And then weight 2 is this one. So weight 2 would be acting at 42 plus 14, that would be 56 divided by 2, 28. So that's just an issue of area times length times width times 24, acting at 35. Is that right? Let's see. How is that 35? Weight 2. This would be 42 plus 14. That's not right. 42 plus 14 is 56, right? 56 divided by 2 should be 28. Okay, let's see. I don't know what is that, acting at distance 35 from the toe. Or we are talking about horizontal height. Are we talking about, where's the reference to this values? Ah, okay, yeah. So, sorry, the reference here is here. We're talking about horizontal, we're not talking about height. Sorry, so that's okay. So this is the toe. So we are talking about the distance. Okay, let me highlight with the pen. So we are talking about these heights, not vertical heights. All right. So this is what is they're saying 21, and this is, so that makes sense. That makes sense. Sorry, 35. So that makes sense. That makes sense. A lot of sense. We are not talking about the the heights. So okay. Then weight 3. I'm just following for you to so you can see how we get this. So weight 3 is just the area, um, of this small section, which is basically uh, a half times base times height, of course, times the volume, which is for 80, acting at 39.7 meters from the toe. So I think that is fairly straightforward. And then the upslope or horizontal, of course, a half times the weight of water times the height squared. You can see there the height is 53. So no, it's nothing unique. The vertical forces PV1 and PV2, uh, I think is pretty well demonstrated there. So just the area of those sections whose dimensions you do have. So then PV1, this is how to calculate PV1, PV2, and then so acting, you can find this, what I was telling you. So again the centers of these ones, I mean, it should be fairly straightforward. So the center of mass of this one, the center of mass of this one, will of course with reference to the toe. Again on the downslope, the same idea. So on the downslope you have been told here. So if you have a question, these are the same things that are gonna show up in the exam. So please, if you have a question, you can ask here to make sure that it's very clear what we are talking about. Now, the funny bit is there are some people just joining class now, so uh, and we have done some bits. So I think I've demonstrated enough how to do this. The rest, you can go spend some time to see. So the downslope, again, you can see there how to calculate the horizontal force and the force above uh, the force above the base, force of water, I mean the height of water above the toe on the downslope side. So these are the values given there. You can check for yourself. So I tried to give you several examples to make sure, just to make sure that you're able to figure out what is happening and make sure you can learn. And please, if you have a question, you can ask. So maybe I think we can take a break for we are on slide 16. We can take a break for 5 minutes and resume at 8:26. Okay.
I can hear you.
Okay, good. So we move on. So this is now to demonstrate the second part, the overflow section, how to deal with it. It's gonna be, I believe, more clear if we are talking about, um, excuse me. If you see with an example, it's easier. So the dynamic force on the curved surface, take the coefficient of distance on the spillway to as 2.1. The radius of the bucket curved section is 4 meters. The discharge intensity can be calculated from the formula shown. Of course, it's simpler when you're given the how to calculate the discharge. So this is 2.1 times the height is 1.5. Of course, based on the okay, on the driving head. So 3 point Q max is cubic per meter cubed. A short form of cubics per meter cubed. Of course, per meter, because we said, you remember we said that. So just to be absolutely clear, we said that we are doing this per unit meter. So this is x, y. So in the z direction, that is 1 meter. So that's why the reason for this. So let D1 and D2 be the thicknesses of the sheet of water at point 1 and 2, the references, respectively, and V1 and V2 the corresponding velocity. Applying Bernoulli's equation to point 3 on the upstream water level and points 1 and 2, taking datum at the riverbed. So the all whatever we are saying 1, 2, and point 3 is your reference, of course. The all the principle of conservation of energy is maintained. So I think these details you see for yourself and should be able to figure out uh, what is happening there. So I think the example you can see you can check for yourself to see how actually you can manipulate such kind of information if given. So far, excuse me. If you have a question, please you can shoot about the what we have covered so far, because now this is an interlude And of course, next we are going to the now hard design, the calculation part. So silence means everyone is fine. Make sure those who just came in, make sure you record your attendance. And we have a cut on 28 for geotechnical engineering, so note that in your calendars. So the uplift pressure sorry, the uplift pressure, we just a minute. Okay, the uplift pressure, the water enters the pore, cracks, and fissures within the body of the dam at the interface between the dam and within the foundation. I think we already talked about this in the introduction. Because the water is under pressure, it creates an uplift pressure on the dam. The pressure acts in all directions, but the pressure acting upwards is the most important for the design. Of course, these are basic principle from Pascal's principle. Water pressure is acting in all directions equally, so this is the beauty. But we are concerned with the upward pressure, because if it becomes too much, greater than the self-weight of the dam, then your dam will fly, will fly. And this is also sometimes a problem in the foundation. So the computation of the forces due to uplift requires determination of the area on which it acts and the intensity of the uplift pressure at various points. This is the same idea of the, I think we already talked about this in part. You can draw the flow net and then to find the pressure points, and then you can find the uplift force. Area factor, the uplift pressure generally does not occur in the entire horizontal area, because in some portions there are no pores in which water can enter. The fraction of the total area in which the uplift pressure acts is called the area factor, recommended an area of about a third to two-thirds for both concrete and rock. So intensity of the uplift, I think this is, we just, okay, let's just go through so that you probably have a better, clearer idea. But you can see just the same thing we talked about. The intensity of the uplift pressure at any point depends upon the depth of the water at that point. At the base of the dam, the intensity of the uplift pressure of the upstream is equal to the hydrostatic pressure. Okay, too many stories. So let me show you. I think just remind you, because you already know this. So if you have you normally we use the flow nets, and you draw the flow nets like that, like this. So here, also once you draw the flow nets there, so here you are lucky, because you don't need a lot of points. You just need that point. So this point and that point. So once you do that, you so here at the head loss, here you have to say h. Those The head is lost in minus h1. You remember in our case, so if this h is 0, then the head is just h. But now h minus, okay. Then is lost in how many? 1, 2, 3, 4, 5, 6. Okay, 7. I think 7. 1, 2, 3, 4, 6, 7. In 7 equal steps. So if you want the head loss at point A, would simply be h minus this. So that's at point A, the head at point A. At point B, I think those are 6, so that would be h minus 6 into h minus h prime minus h prime over 7. So this is the head loss at point B. So then you draw the pressure diagram. Let me use a different pen. Um, the pressure diagram there, and then the height at this point is that, and then the height at this point is that. Then of course there is a linear pressure variation, and then you find the area of this pressure diagram. That would be your uplift force. Of course, the uplift force would be acting. If you want to know where it's acting, you divide this into okay. I think already been shown. So the rectangular, of course, the uplift force is acting at the center, at the L over 2, B over 2, sorry. And then for this triangular section, it's acting at a third or from one of the edges. So using the same idea that so force the area of this, so force acting on this. So if you take the reference here, so let me just say the point at which it's acting is some x bar there, which we don't know. So the uplift force, let's call the uplift force from this U1, and then the uplift force here U2. Those are just the areas times the area of the pressure diagram. Of course, times the gamma times gamma. No, no, no. The area is okay, not gamma. You don't multiply gamma. The area of the pressure diagram, that's okay. So now to find the centroid would be, of course, U1 times B over 2 plus I need to change this color, it's not gonna be visible there, plus u2 times b over 3 of course it should be u1 plus u2 times x bar. The only thing you don't know there is x bar. You know u1, u2, all these things you know. So that's the point. So this is the same idea with even the earth dam. So that's how to calculate the uplift pressure, and it seems that this part is repeated. Yeah, that part seems to be repeated, so we need to delete it. Wait. Uplift, so that I think this part, where is it here? Yeah, this is repeated, so delete it. Yeah, so that's how to get the intensity of the uplift. No, that's how to get the uplift pressure. So we did talk about this. So intensity of the uplift pressure, how to calculate, I think we already talked about that. Now for this one, because you can see we have different sections. So let's just follow. So the total uplift, I think I already covered this. This is just the explanation for this for what you can see on your screen, which I think I have covered. So just telling you, if you want to find the total uplift, is you add the u1 plus u2, which is gamma h times p plus a half, of course, the area, basically the area of the pressure diagrams, that's all. So where u1, I think there's some notation issue there, here, u1, I mean, is should be fairly clear. And if you have a question, please you can ask to make sure we're understanding each other. So this, of course, the distance is b over 2, and the 2b over 3, I think you know that from the top. So the uplift pressure in the body, the distribution on any horizontal plane within the body of the dam is found the same way, taking the corresponding pressures at the upstream and downstream forces. For example, at depth below the water surface, where the width is equal to b, the tail water depth is h. So anyway, I think you get the idea. If you have a question, you can ask. And I think this one we have done several times, or at least we have demonstrated a number of times in this class. So effect of drains on uplift pressure. To reduce the uplift pressure, drains are formed through the body of the dam. I already said this. So to because of the water is trying to flow uh, from this end to that end, because of that action, of course, pour water is trapped and then tries to cause uplift. So to reduce this, you need to provide some drainage so that the excess pour water pressure can flow away. So these drains are formed to the body of the dam according to some repetition there as well. I should delete this one. Which one? Drains of okay. Let me delete this. So according to the U.S. Bureau of Reclamation recommendations, the uplift pressure at the line of the drain is equal to the hydrostatic pressure at the downslope face plus one-third of the differences of the pressure at the upslope and the downslope faces. So this that whatever we have said is this. So these are some recommendations from experience. So this is how to. So probably with this you don't need to do the flow net, and then what we have demonstrated. So this is something probably they have known from experience, and they have put it in the code. So maybe they have observed this kind of behavior. The uplift pressure intensity at the line of drains is given by, of course, this is the static water pressure, which is basically the gamma times HD, and this, if you substitute the salient values, that's how to get the values. So HD is the uplift pressure head at the line of the drains. Again, I have included sufficient examples for you demonstrating how to solve these problems each at a time. So I've gone through this painstaking process just to make sure you can we can demonstrate these formulas, and then you can have a very good understanding. And so if you follow this, you should have no problem. And I will insist, please make sure you follow, because the same things are going to show up in the exam. And of course, I wish that everyone passes. So this is why I do this kind of painstaking work. So you can see the example is very simple. So I don't want to go so much into the detail, because it's the explanation, I believe, is quite clear and self-explanatory. Of course, if you have a problem, you can always reach out, but you can see there is good demonstration on the PowerPoint. So then there is the wave pressure when wind blows over the water surface of the reservoir. It exerts a drag on the surface due to which ripples and waves are formed. When these waves strike the upstream face of the dam, some spelling issues as well. Let's see, where is that? Where of the dam? The cause of okay, so due to the wave, pressure is horizontal and is computed. So the wave pressure is horizontal, of course, and is computed. You'd expect some equations, of course. Height of the wave, the force depends upon the characteristics of the waves. So, for example, we can calculate the height of the wave as shown. Let's correct the these notations just to be absolutely clear what we are saying. And if f so fv, um, that should also be no, that's sorry, that's okay, because that's the velocity. So now uh, so this is the height of the wave is found by from this formula. Of course, if f is the length, this is uh, the length of the, how can I say, the this theoretical length of the wave, you know, the so that would be considered f. So if so these are the formula, so the cut the, the important part or the reference is 32 kilometers. So if the f is less than 32 kilometers, then this is how to calculate the height of the wave. If if f is more than 32, this is how to calculate the height of the wave, of course. So this is two things. So if you want to find the force of the wave, consider the height of the wave depends on the length. So HW is the height of the wave of height in meters. F is the straight length of the water expanse measured normal to the axis of the dam in kilometers. I think I already showed you. And V is the wind velocity. So you can see the height of the wave depends on the length of the straight length of water expanse and the velocity of the dam. I mean, sorry, the velocity of the wind. So if you want, so you need to know the F and the V, so that you can calculate the height of the wave. So the wave pressure distribution, the actual distribution is difficult to determine, of course. The total height of triangle is about 5/3 or 5/3 of the height of the wave, with a height of 4/3 uh, HW above the still water level. We of course the wave is usually kind of a sinusoidal thing. Sinusoidal has something to do related to the sine wave. So we expect some trigonometric expression, but we are heading there. So so the maximum pressure intensities T occur at a height of HW of an eighth of HW above the still water level, and is given by 2.4 gamma H W. All right. Why do I have a feeling that one of that? Yeah, some have to be uh, yeah, some have to be. Okay, let's copy this one. It's refusing to cooperate. So this is how to get the pressure from the wave. Of course, these are empirical relation. So you need to know. The line of action of PW is at the centroid of the area ABC. So area ABC, area ABC. So if you want to understand this part, you have to refer to the diagram so that it makes things clearer to you. So that which is at about 0.375 HW above the still water level, the total water pressure force is given by these expressions, and I think something is not right. Is that V? 5/3. Okay, maybe it's correct. 2.4. Yeah, so that V maybe is not there, I think, because this is gamma. So this is not right. So this is supposed to be this here. Yes, so that's how we end up here. I mean, the expression should be uh, straightforward. Another example to show you. So the first thing, if I were you, you can see F is 100. So you remember, then you need to remember these previous equations, and then so again you have to go through the example to get a better understanding. Then we have the silt pressure. All rivers carry a large quantity of silt during floods. The silt is deposited in the reservoir, of course, on the upstream of the dam. This silt exerts the earth pressure on the dam. As the silt is submerged, the silt pressure is computed assuming the submerged condition. It is the usual practice to assume that the silt is still fully saturated, cohesionless soil. The silt pressure can be evaluated in two cases. If the upstream face of the dam is vertical, the force is horizontal and is given by, of course, this is related to uh, the the earth pressures, if you remember, and this is the area of the. So okay, I think maybe there's a diagram that will make it clearer. The same idea of the earth pressure distribution. So I have the force. So if this is the high, if this is the depth, so this is the height of the silt. Of course, the distribution, if you remember you should remember the earth pressure distribution would be the same here. And of course, you know that the Ka from Rankine, if you remember your is tan squared tan squared 45 minus 5 over 2. You should remember this, the coefficient. So this is the idea, in fact. And so this is the Ka, and you can see that is none other than the area of the pressure distribution diagram, such that at the bottom here, at the bottom here, this would be gamma S times Hs, and if this is Hs, then the pressure of that, the area of that diagram is half Hs. Hs, you can see that. So that, and this is the coefficient of the earth pressure. In which case, sorry. So yeah, so this is, I think this is the same idea. So Ka is the okay, something akin to the coefficient of earth pressure. I think this is also the same as 1. Okay, 1 ton. Anyway, this is how to calculate Ka. Sorry, there's an issue there with the notations. Yes, here. Uh, okay, let's copy this one. Okay, so this is the same idea of the lateral earth pressure, and of course Hs is the depth of the silt above the bed, and phi is the angle of shear resistance, or the angle of friction of these the silt. So if the upstream face of the dam is inclined, the vertical component of the PV is equal to the weight of the submerged weight of the silt in the area. So again, the same idea. I just find the area times the gamma of the silt. So the same idea with the water. So ice pressure in cold climates, ice is formed in the reservoir, and the reservoir surface gets covered with sheet of ice. There's some issues with the yeah with the there's some issues with excuse me, with the commas and full stop seems to be put haphazardly. The thickness of ice depends upon climatic conditions. Subsequently, when the temperature of the atmosphere rises, ice sheets expand and cause thrust on the dam, because the coefficient of thermal expansion of ice is about 5 times that of concrete. As the temperature falls, the ice sheet contracts and cracks, and these cracks subsequently get filled with water. The magnitude of force due to ice pressure depends upon the following factors. So this just so you know. I told you maybe we don't experience this in Kenya, but you might find yourself in Iceland or in some other country or in Canada. So you will see, you will have an idea at least of what to do. Of course, we know that when ice expand, I mean ice, when water freezes to ice, it expands. Of course, with the expansion comes some additional pressure. So the magnitude of the force of the ice depends on the thickness of the ice. Thickness of the ice in particular reservoir depends upon the number of factors and cannot be easily estimated. Generally, it is obtained from existing records in the region. Excuse me. The thickness is usually not more than 1 meter, but in sub-zero regions it may even be 2 meters or more. Now, the lucky thing is that you know the anomalous expansion of water. So ice can only form on the upper surface and cannot go very deep because of the anomalous expansion. So, and of course, that will cushion or insulate the other layers. So again, that is also something God maybe was very intelligent, because then if the lake were to freeze, then the aquatic life would be in danger. But somehow God knows, so that if the temperature is freezing, uh, we are undergoing freezing temperature, only the top part freezes, then the lower layers are cushioned, and then aquatic life will continue. So the resistance of the resistance of rim walls. The ice pressure exerted on the dam depends upon rigidity of the rim walls of ice. If these walls are strong, the maximum force is caused on the dam. On the other hand, if these walls are yielding, the force on the dam is reduced. And some of these are quite difficult to estimate, in fact. Rate of rise of temperature, the greater is the rate of rise of temperature, the greater is that correct English? The greater the rise of temperature is, I think that's the correct one. The greater the rate of rise of temperature is, the greater is the force. The greater the force of the dam is. But you cannot end a sentence in a proposition. So that's okay. That should be fine. The greater is the force on the dam. The average value of 250 may be taken so as an ice force. So because some of these values are very difficult to estimate, we just take some empirical values. Probably these ones are from some reference or some researcher who has worked with, or some experience. So wind pressure acts on the exposed surface of the dam when wind blows. Generally, the wind pressure is not significant for the design of gravity dams, and it is therefore neglected. However, in the design of gravity dam, the wind pressure can be taken to of 1 to 1.5 kilonewton over the area exposed to the wind. Actually, yeah, but as an engineer, you need to be concerned of everything else, because in any case, the you remember the if that's your dam, the part exposed to the wind actually relatively is very small. So usually you neglect. But if for some reason you have to talk about wind forces, then you take that the distribution of the surface, I mean uh, the load is 1 kilonewton per meter squared. If you were to take it for argument's sake, in any case, the the height. Okay, yeah, that's all what is to say. But typically you can ignore, because the free height left to the wind force is very small. Now here, earthquake forces, again in Kenya we don't need this, but you still need to have an idea. This is in Kenya, but somewhere else you might need the information. So effect of horizontal acceleration, actually we need it, but not that much. That's the point, because actually earthquakes also have occurred. Minor earthquakes have occurred in Kenya. Effect of horizontal acceleration. The horizontal acceleration can occur in either upstream or downstream direction, because the dam is designed for the worst case. The horizontal acceleration is assumed to occur in the direction which would produce something is wrong. I think we should produce the worst at the so let me add that we should produce the worst load combination. The directions are different for reservoir full and reservoir empty. So here again you have to consider whether the reservoir is full or empty, because those have of extreme load, I mean load variations on the dam. So again, when the so reservoir full condition, for the reservoir full condition, this is the worst case scenario, occurs when the earthquake acceleration acts towards the upstream direction and the corresponding inertia acts in the downstream. Of course, the depends whether the earthquake is coming from upstream or downstream. But of course, it would be worse if the earthquake comes like there's a slope, from because of course you know that if there is some leanings, for example, the flow of water from upstream to downstream, the greater the slope, the worse are the conditions. So this is the same idea. So if there is some slope and the earthquake comes the direction of upstream direction going and downstream, that would be the worst case scenario. Of course, if it comes from downstream going upstream, it would be acting against certain some slope, so that would help a little bit to protect the dam. So the worst case scenario is when earthquake comes from upstream to downstream. As a reservoir empty condition, for the reservoir empty condition, the worst case occurs when the acceleration due to earthquake act towards downstream direction and corresponding at the inertial forces act in the upstream. So for a reservoir empty, the worst earthquake is in the opposite direction of the reservoir full uh, case. There was an issue with the with punctuation. Now the horizontal force, so I need to keep the horizontal force due to an earthquake is the same as the mass times the horizontal acceleration. I think you have done this in if not, I think probably introduced to you in structures in mechanics. Not, is it mechanics? So there is a structural course where you do something like this. Why is this thing refusing? So let me copy this one, copy and put here. Yes. Yeah, so the mass times the horizontal acceleration. Now these ones will be given to us by geologists. The horizontal acceleration of earthquake, because earthquake acceleration is expressed as alpha h times g, and mass is equal to mass to weight divided by g. Yeah, so you can see uh, okay, two things. The earthquake is something like maybe it's two. So normally the net effect is that these forces are acting horizontally. So there is some horizontal acceleration, alpha h, and then there's also a vertical acceleration, uh, alpha v. Now the worst is the horizontal acceleration, because that one causes shear forces on the structure of the soil and our buildings as well. Of course, the vertical acceleration, usually in most cases this is higher than this, so we are always worried only. Okay, sorry. In most cases this is higher than alpha v, so we are always only worried about the horizontal direction. However, in some cases both vertical and horizontal are bad, are serious. So you need to consider both. But more in many cases, we are only concerned. What happened? We are only concerned. So this, we are only concerned of the vertical case. I mean the horizontal case, the horizontal acceleration case. So this is just to explain what we're talking about. So the horizontal force is mass times acceleration, like I've said. Because earthquake acceleration, I think this is also, this is repeat, is it? This part is repeated, so we have to make it right. So the note that the constant value of horizontal acceleration is between 0.1 g to 0.15 g is assumed for high dams in seismic areas. Even for dams located in the regions not subject to extreme earthquakes, a value of 0.1 g is sometimes taken. However, for dams located in non-seismic areas, earthquake forces are neglected. So this is the idea, and in our case, in most cases, you will ignore the earthquake forces because they are not the dominant factors in design. Remember, I'm saying in some instances. So as an engineer, you have the information. When you are faced with such a scenario, you have to make your judgment. You have to assess the earthquake forces. Are they significant? If not, then they can be ignored. Of course, in certain uh, areas prone to earthquake, especially the Asia, those ones is a must. The part and parcel of design codes. Also, I think in US, certain parts of US, the West California, in fact, there are faults running there. So, if for some reason you are there, there's no way to escape. You have to consider earthquake forces. Now, methods of determining the value of seismic methods of wow methods of determining that's an issue with serious determining. So we can save this one. Methods of determining the value of seismic coefficient alpha. Seismic coefficient method for dams up to 100 meters in height. Uh, the horizontal seismic coefficient alpha h at the top of the dam is taken as 1.5 times the seismic coefficient alpha. The coefficient reduces linearly from 1.5 alpha to 0 at the base of the dam as shown in the figure. The inertia force for any part of the dam above a horizontal section as well as for the entire dam above its base may be computed by integration. So usually the earthquake forces, if I think you should have done, gets worse with the increasing height. The same to the bit. So if you have a tall high-rise building, uh, the the earthquake forces will get worse as you go up. So here so this is the worst case. So it reduces linearly as you go down. This is the same idea with the wind force. I'm sure you have done that. It's the same idea here. So we are saying, so we know the maximum and the minimum. So the intermediate, if you're interested, you can obtain through integration. However, for engineers, we like to make things simple, so we can make certain assumptions And of course, we are also supposedly good in math, so we don't fear integration if that is the case. So there's an example here, portion from the top. So let's see, by integration, so portion from the top, section 1 1, 1 1, you can see from the diagram there, and at depth h1. So let us consider a small portion of the dam dy at the depth y below the top of the dam. The force of inertia acting on this small portion would be, so first, I think there was some punctuation problem. Where was that? Oh, here. My mouse is misbehaving. I don't know why. There's a punctuation problem. Where is that? Here. Yes, here. Excuse me. So now the force is just the area, the volume, of course. So let's see here. The area, we're talking about this area. So the force would be, first of all, the area is b1 times dy, of course, times the inertia, the acceleration from the earthquake. So b1, and we are assuming a unit. So I think this is the reason. Yeah, b1. Okay. So now times 1, because of the direction perpendicular to your eyes, we said is 1. So this is kind of the volume. So the length times width times the height, kind of the direction in your, of course, times the density of the concrete, or unit weight of concrete, and of course times the coefficient of concrete. So alpha hy is the horizontal seismic coefficient at depth y, right? So that's what to do. So if we make this equation in terms of alpha hy is as the uh, subject of the equation, then this is we end up with this, and then we say alpha hy divided by something is doesn't seem right there. Let me see. Alpha. Okay. So this is how to get the value of alpha hy from. Okay, we can substitute here because the this is from similarity and congruency. You have learned this. But if you compare this from here is alpha is 1.5 alpha, the alpha h is 1.5 alpha, and here is 0, and the height is h. So by similarity and congruency, you can get alpha hy there in terms of h and alpha 1.5 alpha. So that's what we are doing here, and then you can substitute back in question 19. So by integrating, so remember this is df1. Of course, we are always happy to integrate to remove the delta. So if you integrate df1, you get f1, and then here you have a nice equation in terms of dy, which you can integrate, and I think that's a very simple integration. We no need to get so much into the detail, and so this is your solution for the first one. So the moment of force df1 about section 1 is given by dm1 again. Happy to integrate. Excuse me. Excuse me. So from the portion 1 at the depth height to section 2.2, at depth h2, let us consider small portion of the dam of height dy lying between 1 and 2 at the depth y below the surface. The inertial force is given by, so the so we found the force, the moment as well. Now we are saying portion 1 at a depth h1. So still referring to the uh, this uh, this portion 1. So we want to integrate the point here. We want to integrate from point 1 here to point 2. So this is what we are doing here. So f1 plus the form. We already established the force equation here, right? This is the force equation, but here we are integrating from 0 to h1, right? So if you want, the idea here is to show you, if you want the force acting on any section, uh, not including the entire section of the dam, that's the point. So if, for example, you are only interested in the force from here to 2, excluding this lower part, you see. And also the integration helps us to, because you can see these sections are different, so you can integrate probably the triangular section first and then the trapezoidal section later, so just to help you know. So here at section 1, from here to 1, we already have f1. So to get the difference between 1 and 2, this is what we are doing. So f1 plus the integral between h1 to h2. Sorry, this is the equation here. So this is what we are doing, whereby by is the width of the dam uh, uh, section at depth y below the top of the dam, and is given by, so that's by, and I think in the there's some issue with the um, yes, this is not, yes, is this not correct? Yeah, so that's, and then we can get by as shown in the equation there. Excuse me, where n is the slope of the downward slope. Again, by the by you can get from congruency and similarity, because you know this is b1, right? b1. So at any point y, from similarity you can get the similarity and congruency. You should be able to get the so if it's a straight portion, if there is no slope, because n is the slope, if there is no straight portion, then of course this value n is 0, and then the by is the same as b1, as you can see. So the f2 uh, f2 then we can calculate as shown, of course from the integration. Then the moment of the force section 2 is given by, again, the same idea. The you can get moment 1 plus f1. Okay, this is moment 1 basically, then times the integration. No, this is the moment 1, and this is the integration, and then getting the moment. So this is basically the equation of the moment, but to integrate from h1 to h2. So response is, so this is one way to get, you can resort to integration to get the forces and the moments. This is just to demo. Of course, there will be plenty of examples later to demonstrate how this can be used. So you can use integration, that's the first point, and it has been sufficiently demonstrated to get the force and the moment. So there is what is called response spectrum method. In the response spectrum method, the value of the horizontal seismic coefficient alpha h is taken equal to the value of the coefficient seismic coefficient alpha, Now, these values, don't worry, are given by geologists, those people who monitor uh, uh, earthquake will tell us, or if you need the data, you can go to the ministry concerned. And in countries that actually in Kenya, we should have this in our own codes. So these are values that easily obtained. You can easily obtained in the code. For example, in the euro, I think Kenyan we have some. Yeah, we have some earthquake. I don't know how to call it a code, but there's something on earthquake which you can get some values. In the US, in the BS, these values are there. You can always refer to the BS. And of course, this there are or you can go to the government institutions like the ministry or even the universities that have monitoring stations. Those values you can get. The point is, those values are standard, and you can always find them if you need them. Okay. So this is for this. This is how to get alpha based on some influence factor F naught, and then where this is where B is the soil foundation system factor, the value of which gravity dams is equal to 1, I believe. Gravity dams, so some mistake in spelling here. Where is that? Gravity dams is equal to 1.0. So okay, so these are so for gravity dam, that value is 0. I is the importance factor, the value for which gravity dam is taken as 2. And F naught is seismic zone for average acceleration spectra. The value which is obtained from table 1, there's a table. Of course, here now, these values are already established. You can get from these such tables, which are found easily in the code or from the government institutions. So then upon the if the value of which depends upon the natural frequency T vibration of the dam and the damping of the dam, its value is obtained from figure 14. There, figure 14. Yes, figure 14 there, which is known as Hosner's chart. So you can get this from figure 14. So and then the figure 14 is also okay, the value can be obtained from figure 14. That's the point. And this is how to calculate the natural frequency of vibration of the dam, where h is the height of the dam, b is the base of the dam, ec is the modulus of elasticity of the dam. So assuming damping of 5% as suggested by this is the Indian standard. This should also be in the code as well. In the Indian standard, the value of S over G may be obtained from figure 14 for part of the dam up to section XX at a depth Y below the top of the forces Fy and My about the dam as given by. So this demonstrates how to use the chart basically to get Fy and My, and of course there will be uh, enough enough examples to demonstrate this as well. So the S over G. So, for example, say the natural period is what is 8 is 0.8, let's say, and the damping is 5%. Then you can read the value of there. Now, someone would want to ask, because you can see the damping there is 20, 10, 5. So, if for example the damping is 15, so you just do interpolation. So, 15 is between 10 and 20, so you just interpolate and have some value there. So that's it. So this is also a table that gives you the values of alpha naught and f naught for different zones. So these zones, actually Kenya also have this map like this: zone 1, 2, 3, 4. So they are zoned like that based on the severity of the earthquake in whichever area that is involved. Yeah, so these are, I told you, this one you can get from the code. If for example purposes, if you're supposed to use this, you can be you it will be told you'll be told explicitly what the alpha y is, or the I, those values, or at least a formula how to calculate them. Otherwise, there are values that can be determined from the codes. Okay, so this is how to calculate the my, the fy, sorry, the force, and then this is also how to calculate the moment, where the values of coefficient cf and cm depend upon the ratio yh and are taken from figure 15. Is the so h bar is the height of the center of gravity of the portion xx. The total force F and M above the base of the entire dam are given as shown. So this has just some empirical formulas, and so this is based on y over h. You can get those values as c. So here, based on these values, you can calculate. So y and h, you can calculate values of cf and cm. All right. So this is so with this, based on this chart and the, what do we call them? So you can use integration. You can use response spectrum chart to calculate the forces and the moments. All right. Uh, so effect of vertical acceleration. So now we've dealt with the horizontal acceleration. Now how about vertical acceleration? Due to the uh, vert vertical acceleration, the inertia forces on the dam, the magnitude of the force is equal to the product of the mass and the vertical acceleration. Thus, uh, I mean the same idea as what we talked about in the horizontal case. So if the vertical acceleration acts downward, the inertia acts upwards, and the effective weight of the dam is decreased. So hence the stability is reduced. So the idea is, if there is upward acceleration, right, the vibration is trying to bounce around the structure, the dam. So you can see the force is acting, the gravity, the self weight of the dam is acting downwards. The inertia from the earthquake is putting it upwards. You remember, just like the uplift force. So that means the effective weight of the dam is reduced, and therefore the dam might just bounce around and cause problems. So this is what you're saying. Hence, the stability is reduced because in gravity dam, the main stabilizing force is the weight of the dam. On the other hand, if the vertical acceleration act upwards, the inertia force act downwards, and the increases the effective weight. So actually, if the inertia is acting downwards in the same direction as the weight of the dam, then you don't need to worry because the dam is more stable. It will act like some additional weight on the dam, so the dam is firmly on the ground. Otherwise, if the inertia is acting opposite to the direction of gravity, then you have a problem that will lessen the weight of the effective weight of the dam, and therefore the stability issue. So the inertial force act downwards and increases the effective weight and further increases the stability of the dam. So that would not cause us any problems. Note that the modified weight of the dam may be used in the analysis where modified weight. So this is the issue. I've told you if the inertia is acting upwards, it will reduce the effective weight. If it is acting downward, it will increase the effective weight. No wonder you can see here we are modifying the weight of the dam to see how much the inertia is affecting, reducing or increasing. So the modified weight can also be obtained considering the effect of specific gravities. We can take so this is the how to modify the effective weight. So for computing the weight where gamma c and gamma are the concrete and water unit weight respectively. I think something is missing there. That's unit weight. Unit weight. Unit weight respectively. So a constant value of a visit is sometimes adopted in the design of dam. However, the seismic coefficient method should be used for dams up to 100 meters height. So some caveat on how to or when these values are used. However, dams up to 100. Okay. So seismic coefficient method. In this method, the value of vertical seismic coefficient at the top of the dam is taken as 0.5 times the seismic coefficient. Remember we said that for the horizontal coefficient on the top of the dam is 1.5. So the same idea, but here now it's 0.75 times the coefficient, a seismic coefficient determined and reduced linearly to 0 at the base of the dam, the way we've done with the horizontal case. In other words, the vertical seismic coefficient distribution diagram from the top to the bottom of the dam is 1/2 of the horizontal seismic coefficient. So you remember me telling you that the severity of the vertical acceleration is not as serious in comparison to the horizontal one. So you can see the distribution for the vertical case is about half of the horizontal. So response spectrum method. In this method, the value of the the vertical something is wrong. In this method, the value of the vertical at the top of the dam, something is not right there. Anyway, I think we talk about this in the next class. So if there's a question, so you need to note now here in the horizontal case we can use integration to get the forces and the moments. We can also use the response spectrum method. For the vertical case, we can still use the seismic coefficient method and also here the response spectrum method. And of course, the with the each with the associated example, enough example.